Every day, 5.5 million people ride the New York City subway, and the only thing standing between those 400-ton trains and complete disaster is just 2 inches of steel rail. These rails take an incredible beating. 300,000 wheel impacts every single day, temperatures swinging from -20 degrees Fahrenheit in winter to 140 degrees in summer, and somehow they never crack, never bend, never fail. So how do you actually make something that can handle that kind of punishment for 40 years straight? What's the difference between these subway rails and regular steel that would fall apart in weeks under the same conditions? Today, we're going inside one factory in Nebraska where these rails are made, and I'm going to walk you through the entire process from the moment raw materials arrive at the gate to the moment a finished rail gets installed in a New York City tunnel and a train rolls over it for the first time. The factory is in Norfolk, Nebraska, which is a small town of about 12,000 people, sitting in the middle of endless cornfields. And when you drive up to the Nucor Steel mill, you see this massive industrial complex covering 3,000 acres, where every single New York City subway rail is manufactured. What's interesting about this place is that the entire process happens right here in one location. The iron ore arrives at the east gate, goes through all the different buildings and furnaces and machines, and finished rails leave from the west gate headed to New York. The raw materials show up on freight trains that pull in several times a week, and we're talking about 15,000 tons of iron ore in a single delivery coming from Minnesota's Iron Range, which is actually where America's entire rail steel industry got its start back in 1884. Along with the iron ore, you've got limestone coming from quarries a couple hundred miles west, and coke, which is basically purified coal that's been processed at extremely high temperatures. And all of these materials get unloaded and moved to different areas of the plant where the process begins. At the center of the whole facility, there's this massive blast furnace that stands 10 stories tall. And when you're standing next to it, you can feel the heat radiating off the steel and brick exterior even from 50 feet away. Inside that furnace, the temperature reaches 3,000 degrees Fahrenheit, which is hot enough to actually vaporize aluminum, and the way it works is pretty straightforward. Iron ore, limestone, and coke get loaded in from the top, while superheated air gets blasted up from the bottom at 600 miles per hour. What happens inside is that the incredible heat literally rips the iron atoms away from the rock, and all the impurities in the ore rise to the top as this liquid slag that gets skimmed off and actually ends up being used for road construction. The pure molten iron collects at the bottom of the furnace, and you can see it through observation windows glowing this bright orange color as it flows out into these massive ladles that are about the size of a garbage truck. Overhead, cranes pick up these ladles, each one holding about 300 tons of liquid metal, and move them just 50 feet over to the next building, where the real transformation into steel happens. In the building right next door, there's what's called a basic oxygen furnace, and this is where the molten pig iron from the blast furnace gets converted into actual steel that can be used for rails. The process is pretty intense. They blast pure oxygen into the liquid iron at supersonic speeds, and when that oxygen hits the carbon that's dissolved in the iron, it ignites instantly and creates these massive flames that shoot 40 feet up into the air, while the whole building shakes from the noise. The entire reaction takes exactly 18 minutes, not 17, not 19, but exactly 18. And what comes out at the end is steel with a carbon content of precisely 0.75%. That specific number is absolutely critical, because if there's too much carbon, the rail becomes brittle and will shatter when a train wheel hits it. But if there's too little carbon, the rail wears down way too fast and you'd have to replace it every few months instead of every 40 years. The margin for error here is incredibly thin, like thinner than a human hair, because one small mistake at this stage ruins 300 tons of steel that has to be melted down and started over. From the oxygen furnace, the molten steel flows directly into the casting building next door, and this is where it starts taking on a solid form for the first time. The steel pours into these water-cooled molds, And what's fascinating is that the outside of the steel solidifies almost instantly when it touches the cold mold, while the inside stays completely liquid. The casting machine slowly pulls this steel through at about 3 inches per minute, and what comes out is this continuous glowing ribbon of solid steel that looks absolutely mesmerizing as it emerges from the machine. Automated saws cut this continuous ribbon into sections that are 39 feet long and weigh 12 tons each, and even after cutting, they're still glowing bright red at around 1,800 degrees Fahrenheit. These sections get picked up by robotic arms and transferred about 20 feet over to a line of reheating furnaces, where they need to be brought to exactly 2,200 degrees Fahrenheit before they can go to the rolling mill. The temperature control here is measured by sensors 50 times per second, because if the steel drops below 2,180 degrees, it won't shape properly in the rollers. But if it goes above 2,220 degrees, the internal grain structure starts to collapse. So you've only got a 40-degree window to work with in a furnace that's running at 2,000 degrees. The next building overhouses the rolling mill, which is where these thick, rectangular billets of steel get transformed into the actual shape of a rail. And when you see this process in person, it's pretty incredible. The glowing steel enters between 2 enormous steel cylinders that press down with 5,000 tons of force, and you can literally hear the metal screaming as it gets compressed and stretched. It sounds exactly like a jet engine taking off, and the whole floor vibrates under your feet. Each piece of steel has to pass through 22 different sets of rollers, and with each pass, it gets closer and closer to the final rail shape. In the first few passes, the billet gets flattened out and elongated. Then around the 5th pass, you start seeing the curved head of the rail forming where the train wheels will eventually ride. And by the 10th pass, the vertical web section is taking shape. And finally, after the 22nd pass, you've got the complete rail profile with the base that'll get bolted down to the railroad ties. The crazy thing is that this entire rail shape has to be accurate within 0.5 millimeters, which is literally half the thickness of a dime, across all 39 feet of glowing steel. Because if it's off by even 1 millimeter, the whole thing becomes scrap metal, and 12 tons of work goes to waste. After the steel comes out of those final rollers, it's moving along at about 18 miles per hour and still glowing at 1,650 degrees Fahrenheit. And this next moment is probably the most critical 4 seconds in the entire process. Water jets blast the top surface of the rail at 800 pounds per square inch of pressure, and the temperature of that head section drops from 1,650 degrees down to 400 degrees in just 4 seconds flat. What this rapid cooling does is transform the molecular structure of the steel at the surface level. The head becomes extremely hard, almost like glass, while the web and base sections cool more slowly and stay flexible. This creates what's basically a hybrid material, where the top 2 inches are harder than a knife blade, so they can resist wear from 50 million wheel passes every year, but the bottom 4 inches remain flexible enough to absorb impacts without cracking. If the timing of this water cooling is off by even 2 seconds, the rail develops these microscopic fractures that you can't see with the naked eye, but will cause the rail to fail within months instead of lasting 40 years. Once the rails have cooled down, they go through cutting and drilling, where carbide-tipped saws cut them into their final lengths. 39 feet for sections that'll be installed on curves, and 78 feet for straight sections of track. Then, drilling machines create 38 precisely positioned holes along the base of each rail, and these holes have to be accurate within 0.1 inches, because each bolt that goes through them will be carrying 12 tons of lateral force every time a train goes around a curve. So if even one hole is misaligned, it creates a stress concentration point where the rail will eventually crack and potentially cause a derailment. And there's a very specific reason why the quality control that comes next is so incredibly strict. On August 28, 1991, it was a typical Wednesday morning rush hour at Union Square Station in Manhattan, and a southbound number 4 train was coming into the station when suddenly the train lurched violently and derailed. 5 people were killed, over 200 were injured, and the investigation revealed something terrifying. The rail had developed a microscopic internal crack during manufacturing, something so small it was invisible to the naked eye. But under the constant stress of trains passing over it day after day, that tiny crack had slowly grown until the rail finally gave way. That tragedy completely transformed how subway rails are made and tested. Today, after cutting and drilling, every single rail goes through what's basically the most thorough inspection process you can imagine in Building 6. Ultrasonic testing machines send sound waves through the entire length of steel to detect any internal cracks as small as 0.1 millimeters deep. Defects that are completely invisible to the human eye, but could be catastrophic. The rails also get checked by laser systems that measure straightness within 3 millimeters across the entire 39 feet. And surface scanners look for any pits, scratches, or rough spots on the head where the train wheels will be riding. The rejection rate at this quality control stage is 11%, which means 1 out of every 9 rails that make it this far never leaves the factory. They get sent back to the blast furnace to be melted down and started over from scratch. It's expensive, it's time-consuming, but after what happened at Union Square, nobody in the industry is willing to take chances. Only absolutely perfect rails get loaded onto trucks at the west gate of the plant. The rails that pass inspection get loaded onto flatbed trucks for the 3-day journey to New York City, traveling east on Interstate 80 through Iowa and into Pennsylvania, then taking Interstate 78 through New Jersey, before finally going through the Lincoln Tunnel into Manhattan. They arrive at staging yards in Queens, where they sit and wait for their turn to be installed, because the actual installation work can only happen between 1 in the morning and 5 in the morning when the subway trains stop running and the crews have a 4-hour window to work. Installation teams use hydraulic lifters to carefully position each 2.4-ton rail section in these tunnels that are only 12 feet wide, and then they weld the rails together end to end using something called thermite welding, which is a chemical reaction that produces molten iron at 4,500 degrees Fahrenheit that flows into the gap between the 2 rail ends and fuses them into one continuous piece. After the welding is done, grinders come in and smooth everything down until you can't even see where the joint was. And then workers bolt the rails to concrete ties every 21 inches, with each bolt being torqued to exactly 250 foot-pounds. Not too loose, or the rail will shift around, but not too tight either, or the concrete will crack. When the New York City subway first opened back in 1904, the rails they used would wear out and need replacing after just 3 years, and the trains could only safely travel at about 15 miles per hour through those tunnels. Today, more than a century later, trains run through those same tunnels at 55 miles per hour, and the rails last for 40 years before they need to be replaced. That journey from 3 years to 40 years wasn't just about better steel. It was about learning from tragedies like Union Square and building a system where quality and safety come before everything else. You've now seen how iron ore gets melted in a furnace at 3,000 degrees, how oxygen converts it into steel with exactly the right carbon content, how 5,000 tons of force shapes it into a rail, and why 11% of production gets rejected because only perfection is good enough to carry 5.5 million people safely through underground tunnels every single day. If you found this interesting, subscribe to see more of these deep dives into how the things around us actually get made. Thanks for watching. Every year, thousands of tons of valuable timber around the world get turned into shavings, and only a few pounds become works of art. Picture this. An 11-pound block disappears in 10 minutes, giving birth to an object lighter than your smartphone. But what actually happens in that moment on the lathe? Why does a single mistake, 1 millimeter off, destroy months of work? And why are some species of wood more expensive than gold, unfazed by water, fire, or time? Today, we're diving inside a process where speeds hit thousands of RPM, and wood behaves like metal. Stick around till the end, and you'll discover the secret behind why these materials sing in music, last for centuries, and why craftsmen work with them almost like living beings. The lathe is simple genius. The blank mounts between centers or in steadies, spinning from 50 to 2,000 revolutions per minute, while high-carbon steel or carbide cutters strip away the excess. The craftsman holds the tool in hand, controlling pressure and angle. 1 millimeter off, and everything goes sideways. The process starts with rough turning. The lathe eats wood layer by layer, revealing texture, color, shine. Shavings fly like confetti, filling the workshop with the scent of fresh bark. First, the roughing gouge cuts the diameter down to shape. Then the bowl gouge forms the vessel, and the finishing tool polishes to a mirror finish. The speed is stunning. From an 11-pound blank, in 10 minutes, you get a piece weighing 2.5 ounces. Finish with oil or wax. The wood glows. Not every tree works for the lathe. You need species with uniform grain, no knots, no cracks. Rosewood, or palisander, the king of exotic lumber, hailing from the tropical forests of India, Brazil, and Madagascar. Its heartwood stuns with a violet-red hue that darkens over the years into a rich wine color with black and gold streaks, like a marbled masterpiece of nature. The surface feels oily to the touch. The wood is saturated with resins, which make it gleam like a polished ruby and give off a subtle sweet rose fragrance that lingers in the workshop for hours. Its physical properties make rosewood a turner's dream. Density of 53 pounds per cubic foot, Brinell hardness of 5.5, 3 times harder than oak, yet flexible as bamboo. On the lathe, it cuts like butter. Shavings fly off in thin ribbons, won't clog the blade, won't crack from centrifugal force. The fibers are elastic, so bowls with walls just 1/10 of an inch thick don't split, and candlestick stems survive drops from 3 feet up. The natural oils protect against fungi, beetles, and moisture. Pieces last centuries without varnish. From rosewood, craftsmen make whiskey tumblers for you. The shape is graceful, walls thin enough to see the drink through. The wood's aroma enhances those oak notes. From Indian rosewood, they make sushi sets. Boards, spoons, holders. The contrast of red with white rice looks refined. Often combined with other woods, rosewood plus olive equals a vase with double shimmer. Gibson Les Paul guitars have rosewood fingerboards. The sound is warm, sustained, with deep bass. Stradivarius violins featured rosewood fittings. Today, it's used for saxophone and flute mouthpieces. The material resonates across all frequencies. Rosewood veneers go onto yachts, Steinway pianos, palace tables. The hardness allows polishing to a mirror finish. An unvarnished surface looks like lacquered obsidian. Working it demands skill. Dry in shade for months, because sun exposure causes cracking. Cut with sharp carbide blades. Dull ones bog down in the resins. Final touch, linseed oil or carnauba wax, which brings out the purple undertones. Heat treatment makes the wood fire resistant and nearly black. Red sandalwood, a sacred exotic species from the tropical forests of southern India and Sri Lanka, valued higher than gold thanks to its unique red coloration and magical properties. The heartwood has a rich garnet red color that, when soaked with water or oil, takes on a blood red hue, like a genuine ruby embedded in wood. The surface is smooth, with a subtle sweet aroma reminiscent of vanilla and rosewood. This scent lingers for years, filling spaces with the warmth of the East. Its physical properties make it a turner's dream. Density of 69 pounds per cubic foot. Heavier than oak or rosewood, high hardness, but flexible fibers that allow creating thin-walled pieces without cracking. On the lathe, it cuts slowly, demanding sharp carbide tools. The shavings come out fine and red, like brick dust. The oiliness is natural, so finishing oil just enhances the inherent luster, making the surface look like polished garnet. Best for premium tableware and ceremonial pieces. Turners craft bowls for Ayurvedic ceremonies from red sandalwood. The red color symbolizes Kundalini energy, and the wood absorbs meditation vibrations. Chalices for sacred drinks hold their shape for centuries without picking up odors. In Japan, they carve bonsai stands and teaspoons from it. The contrast of red against white porcelain is stunning. Sushi knife handles are status accessories running hundreds of dollars. Red sandalwood is beloved by masters of the bamboo flute tradition, where the tone comes out soft yet deep. Guitars with red sandalwood fretboards sound warm, with exotic overtones. In India, they make mridangams from it, drums for temple rituals, where the wood's vibrations amplify the meditative effect. Buddhist prayer beads, Hindu jewelry, ritual cups, red sandalwood is considered a conductor of spiritual energy. In Tibet, they carve prayer wheels from it. In Japan, tea ceremony spoons. Veneers go into premium furniture for yachts and palaces. The wood doesn't fear salt water or heat. Processing demands ritual. Dried in darkness for 2 years. In light, the red fades. Cut slowly with sharp tools, the dust is toxic. Work in masks. The finish, natural sandalwood oil or carnauba wax. Heat treatment at 300 degrees makes it black-red, fire-resistant. Turning isn't just about shaping. Masters combine techniques. Roughing cut. They remove bulk, reveal the shape. Deep hollowing. For bowls, goblets, where the tool bites deep, creating walls 2 millimeters thick. Taper turning. For graceful candlestick stems. Final sanding. Grit from 40 to 2000, then oil for shine and protection. Pros add segmented turning. They join rings of different species, like a puzzle. A vase from 10 types of wood. Or texturing. Carving patterns with the tool that come alive when spinning. Heat treatment. Wood heated to 400 degrees Fahrenheit, making it fire-resistant and darker. African blackwood ebony. The darkest treasure of the tropical forests of Cameroon, Ghana, and Nigeria, where it grows slowly, accumulating resinous blackness in its heartwood over years. The wood looks like polished obsidian, deep black with gray or brown veins creating a midnight marble effect. The surface is smooth as glass with a natural metallic sheen. Ebony is so oil-saturated it needs zero varnish. The scent is subtle, earthy, with smoky notes that linger in the workshop for hours. The physics is wild. Density 75 to 80 pounds per cubic foot. This wood sinks. Brinell hardness of 8, twice as hard as oak. On the lathe, it behaves like metal. A sharp carbide tool peels off shavings in thin black ribbons. No vibration, no tear out. Centrifugal force doesn't break the fibers. They're springy like steel cable. Bowl walls a 1/16 of an inch thick don't crack. Stems hold multiple pounds. The oiliness makes ebony indestructible. It won't rot, resists termites, heat, and salt water. Turning artistry at the edge of what's possible. From Cameroonian ebony, craftsmen make spheres just over an inch in diameter with diamond-like facets. Perfect shine without polishing. Sake or whiskey cups, status minimalism, black contrasts with clear liquid. Japanese knife handles, eternal, don't slip in hand, don't dull the blade. Often combined with silver or mother of pearl, ebony emphasizes the whiteness of the inlays. Musical instruments, legendary. Flutes, saxophone mouthpieces, double bass fingerboards, sound pure as crystal, without parasitic resonances. Ebony clarinet mouthpieces cost thousands of dollars. The material doesn't absorb moisture from the air. In Japan, they make kozue from it, bamboo inserts for flutes. Rings, bracelets, pendants. Ebony's harder than bone, polishes to a mirror shine. Veneers for yachts, palaces, Patek Philippe watches. Ebony flooring, an eternal investment, never fades, never chips. Working it, that's where the master gets tested. Dried 3 years in darkness, light dulls it. Cut slow, a dull blade gums up in the resins. Dust is toxic, masks mandatory. Finish with carnauba wax or tongue oil for that wet gloss. Heat treatment at 400 degrees turns it blue-black. There's a metal out there almost nobody ever sees. But it's what turns steel into armor. How is it that just a few grams of vanadium per ton can boost a structure's strength by tens of % and literally lighten the weight of the world? Where does this element hide if it's almost never found pure in nature? And why is it often extracted not from ore, but from dark slag that others consider waste? Today, you'll witness vanadium's journey. Hellish furnaces, blinding molten metal, fire-colored powder, and the birth of ferrovanadium that transforms steel in an instant. And at the end, I'll reveal why control over vanadium is no longer just metallurgy, it's geopolitics. Vanadium holds a special place among industrial metals, though for most people it remains nearly invisible. It's rarely seen in pure form, it's not used for jewelry, and it's barely associated with everyday life. Yet vanadium became one of the key factors in the creation of armored steels and modern high-strength structures, without which bridges, skyscrapers, automobiles, and heavy machinery would be impossible to imagine. The history of vanadium as a metal begins in the 19th century, but it gained real industrial significance much later, when metallurgists understood how even tiny amounts of this element could radically transform steel's properties. In nature, vanadium almost never occurs in its free state. Most of the time, it's found in complex minerals and ores, particularly vanadium-bearing titanomagnetites, and also in magnetite, where it replaces some of the iron atoms in the crystal lattice. The major vanadium ore deposits are concentrated in China, South Africa, Russia, and a few other countries. Mining is typically done through open pit or underground methods, depending on how deep the ore bodies lie. Magnetite ore with vanadium impurities goes through crushing and enrichment after extraction, where they separate out a concentrate with high iron and vanadium content. At this stage, the material isn't split into individual metals yet. It's a complex mixture of oxides. Vanadium's next stop, where metallurgy becomes a true industrial spectacle. Melting magnetite concentrate happens in blast furnaces or electric arc furnaces running at temperatures over 2700 degrees Fahrenheit. Inside the furnace, a mass of ore, coke, and fluxes slowly descends, passing through zones of different heat where solid chunks first sinter together, then transition into liquid. Molten iron collects at the bottom of the furnace, while lighter components, including vanadium oxides, concentrate in the upper slag layer. When the moment of release arrives, the furnace opens, and glowing streams pour out. Liquid slag glows with a blinding yellow-orange light, flows through channels, and throws up clouds of steam when it hits air or cooling surfaces. Right there in that seemingly spent mass lies the core treasure for vanadium production. After cooling, the slag transforms into solid, brittle chunks of dark material, deliberately collected and hauled away for further processing. Next up, crushing. Big pieces of slag pass through crushers and mills, getting ground into granular material or powder. The process hums with machinery, vibrations, and clouds of fine dust, immediately sucked away by filtration systems. The pulverized slag is prepped for chemical treatment, where vanadium needs to be extracted from an incredibly stable oxide matrix. Then the material enters reaction tanks filled with aqueous solutions of alkalis or salts. Under controlled temperature and constant stirring, leaching takes place. Vanadium compounds gradually transition into solution, shifting its color from pale yellow to rich orange or reddish. These visual changes directly indicate metal concentration and allow operators to monitor the process in real time. The resulting solution undergoes several purification stages. It's filtered, removing insoluble impurities, followed by precipitation, adding reagents that selectively bind vanadium. Inside the reaction vessels, a fine precipitate appears, gradually compacting and separating from the liquid. After washing and drying, this material becomes vanadium pentoxide, a bright powdery substance with a distinctive yellow-orange hue. From this moment on, vanadium stops being a hidden component in slag and becomes an independent industrial raw material. Vanadium pentoxide is then used to produce ferrovanadium, or is reduced to its metallic state. This entire sequence, from blinding molten metal to fine powder, vividly demonstrates how, deep within metallurgical processes, a material is born that defines the strength and reliability of modern steel. China produces 70,000 tons of vanadium annually, far exceeding the output of other countries and making it the global leader in both production and consumption of this metal. In terms of consumption, 90% of all vanadium goes into metallurgy, especially into high-strength microalloyed steels, where small additions of vanadium significantly increase mechanical strength, impact toughness, and fatigue resistance of structures. Ferrovanadium production is the critical link between chemical vanadium enrichment and the steel industry. It's in this alloy form that vanadium is most conveniently introduced into steel, precisely dosing its content and ensuring uniform distribution throughout the melt. The primary raw material for the process is vanadium pentoxide, obtained after processing slags or ores, along with metallic iron or iron-containing alloys. The process begins with charge preparation. Vanadium pentoxide is mixed with reducing agents, typically aluminum or silicon, and iron in strictly defined proportions. Next, the mixture is loaded into crucibles or electric furnaces, where conditions are created to reduce vanadium from its oxide state. Temperatures in the reaction zone reach over 3,600 degrees Fahrenheit, and it's at this moment that one of the most intense stages in the entire production line occurs. During aluminothermic or silicothermic reduction, the reaction proceeds extremely rapidly and releases a significant amount of heat. Vanadium oxides surrender their oxygen to the reducing agent, while pure vanadium transitions into a molten state and immediately dissolves in the iron. The result is liquid ferrovanadium with a specified metal content, typically ranging from 40 to 80% vanadium, depending on customer requirements. After the reaction completes, the melt is held to stabilize its composition, then poured into molds. As it cools, the ferrovanadium crystallizes, forming solid ingots or granules with a characteristic dark gray surface. The material is then crushed to a convenient size, packaged, and shipped to steel mills. The main value of ferrovanadium lies in its predictable behavior in molten steel. It dissolves quickly, is barely lost during melting, and allows precise control over microalloying. That's exactly why ferrovanadium became the standard form of vanadium supply for producing high-strength steels, from building structures to automotive components and armored products. The key feature of vanadium is that it works in microdoses. To get a noticeable effect, just tenths or even hundredths of a percent are enough. This means that for 1 ton of steel, only grams of vanadium are used, but those grams can boost yield strength, toughness, and durability by tens of percent. At the scale of millions of tons of steel, this delivers massive savings in metal, energy, and transportation costs. That's exactly why vanadium is often called the metal that lightens the weight of the world. Few people realize that vanadium also plays a role in long-term durability. Its compounds slow down grain growth at high temperatures and under repeated loading. This means structures made with vanadium steels age more slowly, handle cyclic loads better, and withstand sudden temperature swings. In real-world conditions, that translates to years of extra service life without repairs. Vanadium has become a critically important metal for infrastructure, and many countries have added it to their strategic materials lists. Control over vanadium flows means control over steel quality, and therefore over construction, transportation, and defense capabilities. This factor is increasingly shaping the geopolitics of metals. Picture this paradox. How do you cut something harder than any steel? Super hard materials like industrial diamonds or tungsten carbide slice through metal, grind glass, shape airplane turbine blades, and even protect your smartphone screens from scratches. But how do you machine them? It's a hidden science where water pressurized to millions of pounds per square inch, lasers that vaporize atoms, and diamond tools overcome hardness measured 10 times greater than steel. Let's crack this engineering paradox, from labs to factories where the key components of our modern world are born. Industrial diamonds, the hardest natural material on Earth, with a hardness of 10 on the Mohs scale. Tungsten carbide isn't far behind. Its hardness ranges from 1600 to 2200 on the Vickers scale, making it ideal for drill bits, mills, and turbine inserts. These materials withstand temperatures over 2,800 degrees Fahrenheit and pressures of hundreds of tons per square inch. But their hardness is also a curse. Ordinary tools shatter against them like glass on rock. So engineers invented special methods: water jet cutting, laser ablation, and precision grinding. Each one's a hack that bypasses the limits of physics. Water jet cutting. It's high pressure magic. Water under 60,000 psi pressure shoots through a sapphire or diamond nozzle less than 2/100 of an inch in diameter. The jet reaches speeds of 3,000 feet per second, packing enough energy to slice through an 8-inch sheet of tungsten carbide in minutes. For ultra-hard materials, they add an abrasive, garnet, or silicon carbide. The grains accelerate to supersonic speeds and blast away particles of material. No heat, no warping or heat-affected zones, which is critical for turbine blades. Accuracy down to 1,000th of an inch over 10 feet, zero tool wear. When regular water with abrasive can't cut it, say for microscopic holes or perfectly clean edges, lasers enter the arena. Laser ablation works like this. Ultra-short laser pulses hit the material with such force that atoms just fly off, like a shockwave. No melting, no cracks, just clean vanishing, layer by layer. The pulse lasts 1/10 of a second, faster than you can blink. Each flash carries 1 to 10 microjoules of energy onto a tiny spot the size of a micron. In tungsten carbide or diamond, this creates miniature plasma, a hot ionic cloud that rips atoms away. The wavelength of 1030 nanometers in the infrared spectrum penetrates exactly 1/10 of a micron deep and removes an ultra-thin layer with 1 micron precision. The result? Perfectly smooth edges without burrs. In industry, this is done on machines from Coherent or Trumpf. They cut jewelry-grade diamonds for a $50,000 ring, or lab-grown diamonds for semiconductor chips. The process runs cold. The surface heats to a maximum of 100 degrees Fahrenheit, so there's no deformation or material stress. The speed's modest. For diamond, we're talking 1 cubic millimeter per minute, but the precision is surgical. The price tag bites hard. $500,000 for the laser, but it pays for itself in microelectronics. A single iPhone chipset requires processing diamond substrates, where the laser cuts microchannels just 10 microns wide. Without it, you're dead in the water. Here's a cool fact. In 2024, NASA used this tech on Mars rovers. They shaped carbide nozzle parts and heat shields that can take 3,000 degrees without warping. The laser punched thousands of micro holes for cooling, 0 defects. Why's that cool? A regular laser melts edges 50 microns deep, creating a brittle zone. But the femtosecond laser, it's like a surgeon. Energy goes straight to breaking atomic bonds, and heat dissipates instantly. For turbine blades or smartphone screens, this is perfection. The surface comes out mirror smooth. Your phone drops, but glass with CVD diamond coating doesn't scratch. And behind that gleam, a laser that vaporized microns of super hard metal. These aren't just machines. These are genius hacks breaking the impossible. Check it out. Water jet plus laser in one machine. Water roughly cuts through 8-inch carbide. Then a femtolaser finishes microns with insane precision. Hybrid monsters tear through thick turbine blanks for SpaceX, where conventional methods fail in seconds. And there's the brain of the future. Artificial intelligence analyzes every micron, optimizes trajectories, and slashes defects by 40%. Instead of tons of scrap metal, perfect turbine blades spinning at 100,000 RPM without vibration. The global superhard materials processing market hits $15 billion in 2025. That's explosive growth at 8% annually. This surge is driven by key technologies of the future. 5G antennas with diamond coatings that withstand millions of cycles without wear, Tesla electric car batteries with carbide components for maximum energy efficiency, SpaceX Starship nozzles that burn at 5,400 degrees Fahrenheit in the hell of atmospheric re-entry. Every General Electric turbine spinning at 100 to 20,000 RPM. Every Samsung screen with Gorilla Glass. These are fruits of a secret science where water cuts diamond. Lasers vaporize tungsten carbide, and vibrations shatter the unbreakable. The market's booming thanks to demand for ultra-precise parts, gigafactories, Starlink satellites, medical instruments. By 2030, it's projected to hit $32 billion, turning engineering paradoxes into mass production. Every component, from microchips to rockets, carries the fingerprint of this hidden craftsmanship. I can already see a flood of comments like, "Why does this matter beyond smartphones and space?" Heads up, these technologies are crucial even for your health. Tungsten carbide is a hardness monster, But when you try to cut it mechanically, tools shatter in minutes. Electrochemical etching is the hack. Instead of breaking tools, the electrolyte eats the binder, the cobalt, and the tungsten just falls away. The result? A perfectly clean surface. No burrs, no cracks, no heat buildup. And this method has serious real-world value in medical instruments. Surgical cutters for spine and joint procedures. Bacteria can't stick to these surfaces. Surgeons cut through bone cleanly, without microscopic tissue explosions. Sandvik makes endodontic files for dentists, tools that navigate root canals. A regular cutter would snap inside the canal, but these files can twist through 5,000 cycles without breaking. Instead of hammering away, electrochemistry. Turbines fly longer, surgeries get safer, tools last weeks instead of hours. Sounds amazing, but what about emissions, water consumption, energy use? Let's break it down honestly, where the eco-heroes are and where the gray zones hide. Water jet cutting, the king of green. Water is the main weapon. 99% of it recirculates in a closed loop. Garnet abrasive, natural mineral, non-toxic, gets reused up to 10 cycles. Energy, 30 to 50 kilowatts per hour, less than laser. But here's the catch. Old machines dump dirty water into sewers with metal dust. Modern flow, or OMAX, filters are almost 100% zero discharge. Fact, Boeing cut chemical waste by 70% with water jet versus electrical discharge machining with oils. Verdict, green if you've got filtration. Laser ablation, energy vampire, but cold. Femtosecond lasers devour 5 to 20 kilowatts per hour. Lasers, up to 50 kilowatts. Electricity equals emissions unless you're running solar panels. But the upside, zero abrasive, zero water, zero chemicals. There's practically no SAW. The material vaporizes into gas. For microelectronics, it's ideal. Processes diamonds without waste. Verdict, moderate but clean process. Diamond grinding, the dirty leader. Diamond wheels plus emulsions equals tons of abrasive paste with carbide and oils. Every liter of lubricant, a petroleum product, goes into hazardous waste. But there's progress. Minimal lubrication, drops instead of flow, 90% reduction. Cryogenic cooling, no fluids at all. Verdict, dirty, but reforming. Every year, steel giants weighing hundreds of tons are born across the world. Chunks of metal heavier than 40 elephants combined. But here's the question. How do you transform a 400,000-pound red-hot block into a perfectly precise component for a nuclear reactor or aircraft turbine, where even a millimeter of error means catastrophe? Only a handful of facilities and machines on Earth can pull this off. Presses generating tens of thousands of tons of force, buried stories underground. Why a seamless steel shell matters more than any armor, how nations compete for control over these technologies, and what critical weakness of modern civilization heavy forging conceals. You'll discover by the end of this video. If you watch till the end, one fact will change how you think about the strength of metal forever. A chunk of steel weighing over 200 tons. That's like 40 elephants stacked together. Now imagine you need to transform this giant metal block into a high-precision component for a nuclear reactor or aircraft turbine. Sounds impossible? This is exactly what happens every day at the world's largest forging plants, where force, engineering, and precision create genuine metalworking miracles. Among the industry's most remarkable facilities, Japan Steelworks in the city of Muroran on Hokkaido Island holds a special place. Founded in 1907 with participation from British companies Vickers and Armstrong Whitworth, this plant today controls around 80% of the global market for large forged components for nuclear power plants. Here are hydraulic forging presses ranging from 3,000 to 14,000 tons of force, with the largest capable of working steel ingots weighing up to 600 tons. What makes this plant unique? First and foremost, the ability to manufacture nuclear reactor vessels as single, seamless structures. This is critical for safety. Welded joints are weak points where radiation can leak. JSW remains one of the few manufacturers in the world capable of creating such components without any welding. Modern giant presses are engineering masterpieces in their own right. Take, for example, the Schultz steel press in California, which delivers 40,000 tons of force. This machine weighs over 2,650 tons, stands 60 feet tall, and is sunk 8 stories into the ground. To support it, you need a concrete foundation almost 2 inches thick, reinforced with rebar up to 4 inches in diameter. The press is controlled by 12 electric motors, each pumping out 1,200 horsepower, and 24 main hydraulic pumps. When those pumps kick in, the machine can stop 1,700 tons of moving parts to within 1/10 of an inch, all without hydraulic shock that could damage the structure or the workpiece. The precision of this giant is staggering. It can control position to within limits and pressure to within 300 tons of the target value. It's like trying to stop a train 1 centimeter from the mark, over and over, with absolute reliability. The process of creating a massive forged component starts long before the metal ever sees a press. First, a huge steel ingot gets cast. Modern third-generation nuclear reactors need ingots weighing 500 to 600 tons. That's a colossal engineering challenge, making, heating, and moving this little grain of steel that has to stay hot during transport from the steel mill to the forging shop. The steel for these gigantic components has to be flawless. Japan Steel Works uses cutting-edge purification technology, argon blowing to remove impurities, and precise additions of manganese, chromium, and nickel to hit the exact hardness and strength targets. Every single step of the process gets monitored with maximum attention to detail. Once the heated ingot hits the press, the most spectacular part of the process begins. Giant hydraulic pistons, each the size of a small room, slowly descend with incredible force. The metal, glowing red hot, starts to deform plastically, taking on the desired shape. This isn't a quick strike, like old-fashioned hammers. It's controlled, massive pressure that lasts seconds or even minutes. During the forging of a 200-ton workpiece, it needs to be rotated periodically to ensure even processing from all sides. Special manipulators handle this. Enormous mechanical arms that can carefully rotate the white-hot metal giant. These manipulators themselves weigh dozens of tons and are controlled by advanced coordinate systems, ensuring millimeter precision even when working with such colossal masses. Between passes under the press, the workpiece can be returned to the furnace to maintain the required temperature. Forging a large part can take hours or even days, depending on the complexity and size of the final product. The result of this titanic effort? Components our lives literally depend on. Nuclear power plant reactor vessels weighing over 500 tons, capable of safely containing nuclear reactions for decades. Steam turbine rotors weighing over 200 tons, spinning at tremendous speeds, generating electricity for millions of homes. Components for aircraft engines that withstand extreme temperatures and stresses. For the maritime industry, they manufacture crankshafts for ship engines and steering system components weighing up to 300 tons. These parts are used on the world's largest container ships and tankers, ensuring reliability during years of voyages at sea. You'd think forging is just applying force to metal, but it's actually a much more complex science. When metal deforms under immense pressure, its crystalline structure changes. The steel grains align along the load lines, creating a fibrous structure similar to wood. This directionality makes forged metal far stronger in the direction of the fibers than cast steel. Temperature plays a critical role too. Steel that's too hot can become too soft and lose strength. Too cold, it cracks under the press. Engineers must know exactly what temperature to work with each alloy to achieve optimal properties. After forging, parts go through heat treatment, controlled heating and cooling to hit the right hardness and flexibility. Then comes rigorous inspection, ultrasonic scanning to catch internal defects, X-rays, mechanical testing. Not a single hairline crack or void can slip through unnoticed. While Japan Steel Works dominated this field for years, competition's ramped up lately. China poured massive investment into heavy forging capacity. The biggest Chinese presses hit 80,000 tons of force. These are the most powerful machines on Earth, letting the country be self-sufficient in manufacturing components for nuclear power and aerospace. France's Framatome and 2 more Chinese companies round out the short list of manufacturers capable of creating the largest single-piece components for nuclear reactors. This is a global game where heavy machinery capabilities directly impact a nation's energy and defense independence. The history of heavy forging goes back to World War II, when Japan Steel Works manufactured the barrels for the largest guns on the battleship Yamato. Tragically, during an Allied air raid in July 1945, 200 workers at the main plant in Muroran were killed. But the company was reborn and transformed into a peaceful metalworking giant. Today, these technologies continue to evolve. Back in the 1950s, some experts predicted that aircraft manufacturing might need presses capable of 200,000 and 250,000 tons. Such machines still haven't been built. Even the Chinese giants are half that size. But progress doesn't stand still. Tesla has proven that manufacturing massive one-piece components can revolutionize production. The next generation of presses might actually reach that kind of incredible power. Sadly, not every country held on to its heavy forging capacity. The United States, once home to the world's most powerful presses, lost the ability to make the largest ingots. America's biggest steelmakers, like Bethlehem Steel, could only produce ingots up to 380 tons. Not enough for modern needs. That means the US depends on imports for critical components in nuclear power plants and heavy industry. Britain ran into problems too. Sheffield Forgemasters, the company that made components for the Royal Navy's submarines, planned to install a new 15,000-ton press back in 2010. The government initially allocated £80 million, but later cancelled the funding. This limited the country's ability to manufacture the largest nuclear power components on its own. Behind all this colossal machinery are people, engineers, metallurgists, press operators. Their experience and skill are invaluable. A forging master at these giant plants makes adjustments based on decades of experience. He knows how each alloy behaves, how long to keep it under the press, when to rotate the workpiece. Every year, the world mines millions of ounces of a metal most people never even think about. But without it, modern civilization would literally grind to a halt. What if I told you there's a metal hiding in every car that can absorb hydrogen hundreds of times its own volume, operate at temperatures over 5,000 degrees Fahrenheit, and cost more than gold? Palladium seems invisible, but it's what cleans the exhaust from millions of vehicles, drives key chemical reactions, and determines the price of entire industries. Where does it come from? Why is there so little of it? And what hidden detail at the end of this video will change how you think about this metal forever? Stick around to find out. Palladium is a chemical element from the platinum metals group that combines rarity, high chemical stability, and exceptional physical properties. In the periodic table, it has atomic number 46 and a silvery white color that persists even after prolonged exposure to air. At a density of around 7 pounds per cubic inch, it's lighter than platinum, yet strong enough to withstand significant mechanical stress. Palladium's melting point sits at approximately 2,830 degrees Fahrenheit, and it boils at temperatures exceeding 5,400 degrees Fahrenheit, making it suitable for high thermal load applications. One of palladium's most fascinating features is its ability to absorb hydrogen in amounts hundreds of times greater than its own volume. At room temperature, the metal literally pulls hydrogen atoms into its crystal lattice, forming solid solutions. This property is actively used in hydrogen purification technologies, membrane systems, and alternative energy research. Palladium maintains its stability and doesn't crumble, which sets it apart from many other metals. The industrial importance of palladium is enormous. The bulk of global consumption goes into catalytic converters for automotive exhaust systems. In these devices, palladium accelerates the oxidation of carbon monoxide and unburned hydrocarbons, converting them into less harmful compounds. A single passenger car might use only a few hundredths of an ounce of the metal, but with millions of vehicles in play, total demand hits tens of thousands of pounds per year. It's this industry that makes the palladium market incredibly sensitive to shifts in global auto production and environmental regulations. Beyond the automotive world, palladium is everywhere in electronics. It shows up in multi-layer ceramic capacitors, contact assemblies, connectors, and microchips. Thin palladium coatings shield components from corrosion and wear, maintaining stable conductivity even after thousands of power cycles. In electronic components, the metal's mass is usually measured in fractions of an ounce, or even grains, but collectively these amounts carry serious economic weight. Jewelry wouldn't be the same without palladium. It's added to gold alloys to create white gold without using nickel, crucial for people with sensitive skin. Pure palladium is used to make rings, earrings, and watches because it's lighter than platinum and more comfortable to wear. Palladium pieces hold their shape, don't tarnish, and rarely need polishing. Geologically speaking, palladium is pretty rare. Its average concentration in Earth's crust is just a few millionths of a percent. Major deposits are tied to magmatic complexes and sulfide ores, where palladium occurs alongside platinum group metals, nickel and copper. Mining often takes place at great depths, sometimes several thousand feet below the surface, which makes the process significantly more complex and expensive. Because of this, the price of palladium can fluctuate sharply depending on the political stability of mining regions and the state of the global economy. The chemical behavior of palladium makes it valuable in laboratory practice. It's one of the key catalysts in organic synthesis reactions, particularly in carbon-carbon bond formation processes. Thanks to this, palladium plays an important role in the production of pharmaceuticals, agrochemicals, and specialty polymers. Even microscopic amounts of the metal, measured in milligrams or grains, can substantially impact the speed and selectivity of reactions. Palladium's physical properties are equally noteworthy. It responds well to cold working, rolls easily into thin sheets, and draws into wire. From a single ounce ingot, you can produce a sheet covering several square feet. At the same time, the metal maintains high electrical and thermal conductivity, making it useful in specialized technical applications. Palladium is almost never mined by itself. It's a byproduct of nickel, copper, and platinum metal extraction. Everything starts in underground or open pit mines, where sulfide ore is pulled from depths of hundreds or thousands of feet. The ore is crushed and ground into a fine powder, then mixed with water and reagents and subjected to flotation. The result is a concentrate enriched with copper and nickel sulfides and traces of palladium. Next, the concentrate gets roasted in furnaces at temperatures exceeding 1600 degrees Fahrenheit, stripping away sulfur and organic residues. The resulting material is melted, separating into a metallic phase and slag. At this stage, palladium is still mixed with other platinum group metals. Separation begins at refineries, where alloys are dissolved in acids and subjected to multi-stage chemical purification. Platinum, rhodium, and iridium are precipitated sequentially, while palladium is isolated as salts, which are then reduced to metal. The final stage of palladium extraction begins when, after a long chain of chemical purification, the metal has been separated from other platinum elements and exists as salts or spongy precipitate. This material is thoroughly rinsed with distilled water to remove traces of acids and impurities, then dried in furnaces at temperatures of several hundred degrees Fahrenheit. It looks like a gray-black powder with very low bulk density, which doesn't yet have the properties of compact metal. Next, the powder or palladium sponge is fed into melting facilities. Most commonly, induction or electric arc furnaces are used, where the metal is heated in crucibles made from inert materials. The atmosphere inside the furnace is monitored especially carefully. Argon is introduced, or the space is evacuated to prevent oxidation and losses. The temperature is gradually raised above 2,800 degrees Fahrenheit until the palladium particles fuse into a uniform molten mass with a mirror-like surface. When the metal is fully molten, it's held in the furnace for a set period to even out the composition. Even traces of other metals are measured here in fractions of an ounce per ton, so samples can be pulled directly from the melt for lab analysis. If purity doesn't hit the target level, the melt goes back for additional refining. Only after confirming readings above 99.9% is the palladium cleared for forming. To produce ingots, the liquid metal is carefully poured into preheated graphite or steel molds. The weight of these ingots can range from a few ounces to tens of pounds, depending on customer needs. Cooling happens under controlled conditions to avoid internal stress and cracks. After solidification, the ingots are removed, weighed, marked, and the chemical composition is checked one more time. If palladium is destined for catalysts or the chemical industry, it might skip the ingot stage entirely and be turned straight into powder. To do this, the metal is dissolved again, then reduced under controlled conditions to produce particles of a specific size. This powder gets packed into airtight containers, where every single gram carries serious value. Global palladium production is typically measured in the hundreds of thousands of troy ounces per year. On average, worldwide output hovers around 6 to 7 million ounces annually, with more than 2/3 of that volume coming from just 2 countries. Another key figure, secondary recycling, mostly from used automotive catalytic converters, accounts for 25 to 30% of global supply. By comparison, for many other precious metals, the recycling share is significantly lower. In your average ore, the palladium content is incredibly tiny. We're talking a few hundredths of an ounce per short ton of rock, sometimes even less. That means to get just 1 pound of pure metal, you need to process thousands of tons of ore. That's exactly why production costs are so sensitive to energy expenses and logistics.